yeah, let's definitely talk about it after.
Cool.
Thank you.
So for the iClicker, you just have to set it up to get it right, but we will go through and find the whole thing. Okay? So if you set it up, keep going. Right. Who'd like to start us off with a prayer? Thank you.
Our dear Heavenly Father, we thank you for this day and for this opportunity we have to be here in calculus to learn more. And Father, we ask you that might bless us to, with thy spirit, that we can understand what we are learning and retain it, that we can do it on our tests and apply it in our careers, in our lives. And we thank you for the many blessings that we have, and we say these things in the name of Jesus Christ. Amen.
Thank you. Hey, I think I'm going to work on that. While you're working on that, just a reminder about there's a project due tomorrow in lab where you do a numerical integration problem. So you can pick, I suggest picking something where you're gathering data and then you integrate the data using the techniques. Because if you pick something that's just non-integrable, you just type that into a if you have the function, you just type it into the Wolfram Alpha or some other calculator. It'll do the numerical integration for you. So I'll throw out a couple examples of what people have done in the past. So one, I had a geology student. This was not part of the project. They just came to me with this problem. He was doing research for a geology professor who was studying the difference between valleys carved out by glaciers and valleys carved out by water. So if you know anything much about that, valleys that are carved out by water, or canyons that are carved out by water, have a V shape, while canyons that are carved out by glaciers have a U shape. And one of the researchers had walked across the valleys with this was back before everyone had cell phones, but with some GPS that was collecting data every feet telling them their elevation. And so he had this data for these different kinds of valleys or canyons, and they needed to find the cross-sectional area of each of these so they could get a better idea of the volume of the canyons. And so this is a perfect example of a numeric integration problem, because you actually need to figure out what those areas are. So another one, someone that did arc length. What they did was they had a video of the longest NFL kickoff return for a touchdown. The guy caught it like just within a foot of the back line of the end zone, and he ran it all the way back. But he runs all across this field, so this kid wanted to know how far did this guy actually run. So every 5 yards, he got an idea of how far he moved laterally, and took an estimate, and took that data, and then used the surface area formula. So that's another example. And one other thing, so much like the arc length problems, because you have a sum underneath the square root, it's not easy to integrate these things, so they carefully pick problems for you to do. It's very easy to bump into things that are hard, and even if they're doable, there's often a lot of algebraic manipulation to get it into the right form, and that's true with this one. So. Okay, so first let's figure out our derivative. So we're going to get 1/2 the square root of 1 plus e to the x times e to the x. So this comes from the chain rule. And now I can use the surface area formula, which we'll talk about the surface area formula in a minute. So I'm going to have 2 pi times the radius. Well, what's the radius in this case? Let me draw a picture. So this is our function, and I'm spinning it around like this. So the radius is going to be f of x. So it's going to be my function value. So 2 pi times the square root of 1 plus e to the x times the square root of 1 plus that thing squared. So e to the 2x over 4 times 1 plus e to the x dx. Okay? So there's the setup. We go from x equals 0 to x equals 1. Yep.
Why is it e to the 2x?
Because it's this derivative is squared.
Oh, okay.
So I already squared it. So it would be, you could also rewrite that as the square root of 1 plus e to the x over 2 times the square root of 1 plus e to the x quantity squared. Right. So I just put it into that. Great question. Yeah, you don't have to have it scored out. Okay. So any questions up to this point on this problem, on getting the setup? Okay, let me talk oh yes. How do I find the derivative? Okay, so let me rewrite it again down here. So f of x equals the square root of 1 plus e to the x. So 1 plus e to the x. I'm going to think about that as 1 plus e to the x to the 1/2. Right? And then, yeah, then you get the 1/2. And then it's 1 plus e to the x to the minus 1/2. That's what puts that square root in the denominator. And then the chain rule again, which is e to the x. Does that help? Okay, thanks. Thank you for asking that question. Other questions? Okay. Let me talk about the surface area formula for a second. If we have a curve that we're spinning about a line like this, much like with the arc length, we can approximate that curve with straight line segments. And then we can spin those line segments around, and what we get is a piece of a cone. And so you can use your cone formula, surface area of a cone formulas, to figure out how much this is. It depends on what this radius is. We can call that R1, and what this radius is, we can call that R2. And the book derives it for you, and it says if you average those two, and then you multiply by 2 pi, and then multiply by this length here, So let's call that, they call that L. So this is the yellow part, that yellow length. Then we get that surface area. Well, why is that? Well, you can imagine the 2 pi. The 2 pi is going to take one of the radius in the middle and spin it around, all the way around. That's going to give us that distance. And this radius in the middle is exactly this average that we take here of the outside and the inside. So that'll give us the r there. R times 2 pi will give us the distance around. And then the distance around times L will give us an area. So you can actually represent this whole thing as just a rectangle. And easiest way for me to see it is if you take that piece of a cone, slice it somewhere, and then you can unfold it and it'll lay flat. It's just you can think of it as a piece of a paper that's cut out and then rolled up. And each of these edges here and here, those are just pieces of a circle that have the same center, arcs of the circle. And if you cut radially in thin slices, then each of these pieces here looks like almost like a trapezoid, with the outer edge being wider than the inside edge. And then you start lining up those trapezoidal shapes like this. So alternating every other one, and it'll straighten that out. And about how tall is it right here? It's too much of a angle. That's your length. That's your L. The same L that we had up here. And how long is it? Well, the distance around is now this average piece right in there. It's that middle distance, which is the average of R1 and R2 times your 2 pi. So that's another way to see where that comes from. And in our surface area formula, for when we integrate, we actually use every single one of these pieces. So the 2 pi is the most obvious piece. We can pull out the 2 pi. This piece, we have to find a radius. And then this L is both pieces, this dx and this multiplier that we talked about last time. Okay, together this will give us the arc length of a slice. So we need to find the radius of the path that it revolves around, and also this arc length piece. Okay, any questions about the surface area of revolution?
So is the radius always x or y? Because like on a textbook it says it's like 2 pi x or 2 pi y, depending on which axis it's rotated around. Is that always the case?
It could be, well, it could be x, it could be f of x, it could be y, it could be a g of y. So, or, yeah, you could think of it as x or y, but sometimes you have to write y as a function of x. It'll be x or y if you're revolving it around an x-axis or a y-axis. But if you're revolving it around a different line, then it might be x minus 2 or x plus 2 or y minus 1. So we will do an example of one that we can look at both ways. Integrate with respect to x around the x-axis, integrate with respect to x, but spin it around the y-axis. So we'll do an example like that. Okay. Great. Other questions? Yes? Oh, great question. Okay, let me make sure I understand though. So here we have this curve here, and if we spin it around, we get these things. Why do we even have to worry about that angled piece, right? Why not just take, this is horrible, straight around, straight around. Oh man, this is really bad. I need a picture of this. But instead of taking these angled pieces and spinning the angled pieces around, why not just take these pieces? Right? That's your question? Okay. I remember thinking the same thing. Because you think like in the limit, won't that still be close enough? And it turns out not to be close enough. So no matter how small you get on this, I'm going to overemphasize this. Okay, so suppose we are going to approximate this. Here's our dx. And we're going to take this piece here and spin it around. Well, even as we shrink, the ratio of this to this doesn't get close to 1. We still have this, the ratio, we're still going to be off by a factor of, I don't know, like 20% or 30%. And in the limits, you need things like that where the ratio is going to go to 1, where the piece you've picked is going to be basically the same size as the piece you're estimating. And it doesn't work this way if you just go straight. It's not close enough to get us that. Whereas the area of the rectangles, as we get small, the area of this rectangle and the area of this trapezoidish type thing, those ratios do go to 1. As we get thinner and thinner pieces over here, we're off by less and less up here. But with that angled piece, it doesn't get us close enough. So I love the question. Nice. Yes? So it's actually not the. So you can think of it as the midpoint, but what we do. So we're going to say, okay, this is the radius, but the length that we're spinning around is not this length. The length we're spinning around is this length, and as you rotate it down, it becomes a little bit longer. Right. Yeah, and that's the arc length. So, okay, great questions. Other ones? Okay, let's do some fun algebra. Let's actually finish this problem that we started off with on the iClicker quiz. And I'm going to turn you loose. I'm actually going to turn the screen off for a second, and we'll see how far you guys can go, and I'm going to write out one solution here. There are different ways to do this, okay? I don't want to take a lot of time on this problem, but there are a few interesting things that come up here that'll be good for you to know. Okay? Over 4. It's over 4 times 1 plus e to the x. Yeah. start to see what I did there. You don't have to do it this way. There are other ways. When I was in your seats, I would have been able to go through this as fast as I did up there. So this isn't like to make you feel bad or anything like that. Okay. So we can get to some other problems. I don't want to spend a lot more time on this, but I'm going to point out a few things. So I did get a common denominator to put this 1 in here. And then I distributed out my 4. And if you distribute out the 4, you get this. One of the hard things here is to recognize that you can actually factor that down. So if you replaced e to the x with t, it would look like something like 4 plus 4t plus t squared, which looks more familiar to you. So that would be where t equals e to the x. Because this e to the 2x, that is the same as e to the x quantity squared. Right? So we don't often end up with things like this. So you can factor that down to 2 plus e to the x quantity squared. My square root of 4 I pulled out, divides out with my 2 over there. My square root here, and in the denominator cancel out. So you end up with something that's really nice. The square root of a perfect square simplifies to just this, and those are about the easiest antiderivatives to find, and you can finish off from there. So, any questions about this? All right. Let's do another one. Oops. Okay, let's derive the surface area formula of a sphere. Who remembers this off the top of their head? Yeah. So someone said 4/3 pi. It's not the 4/3 one. 4/3 pi r cubed is the volume of a sphere. Okay, but people remember that one better than this one. It's not 1/3. 4 pi r squared. Okay. Now, when you're on an exam and you need to figure out what it is, you can do this problem and figure it out. All right. Or we'll do this problem, you realize how hard it is, and then you'll just remember it so you don't have to do this problem in the exam. Okay. So we're going to take a semicircle of radius r. So y equals the square root of r squared minus x squared. And we're going to split right down the middle. Okay? So you can set this up two ways. You can spin this curve. You can spin that curve around the x-axis. Or you can spin this half part of the curve on the right side in quadrant 1, spin it around the y-axis and multiply by 2. Okay? So we're going to split right here. Okay? You guys spin it around the x-axis. You guys spin it around the y-axis. Okay? This piece is just the upper half. It's really y squared plus x squared plus r squared, and then the sum is plus y. But, so we just have that positive. Spinning it around the wall. Those that are spinning it around the y-axis, you can still integrate with respect to x. You don't have to do it in terms of y. If you do it in terms of y, you'll end up with a deck of the thing there. So, but you can do it by either way. Okay, I'm going to start walking through this. We'll do x-axis first. So if I'm spinning around the x-axis, I have some x value here, and I also have some dx that I'm thinking about, and I need to think about the surface area I get as I spin that piece all the way around. Oops. Okay. Can you guys tell the difference between the blue and the black up there? Yeah? Is that helpful? Okay. All right. So I need to have 2 pi times the radius that each of my, that this little piece here spins around. So 2 pi times, what's the radius going to be for this? It's going to be my function value. So in this case, it's going to be f of x or y. So it's going to be the square root of r squared minus x squared. And then I have my arc length multiplier. So I need to find the derivative of my function. So that's going to be 1/2 the square root of r squared minus x squared times 2x minus 2x. The 2's divide out, so I end up with a negative x over the square root of r squared minus x squared. Nope, because when I take the derivative, I'm only taking the derivative with respect to x. And so this is a constant. So I won't have that. And then I have to square that. So a negative x over the square root of r squared minus x squared, quantity squared, dx. This much is my L, that's the length, and this much is the distance that it travels. And I can go x equals a negative r to x equals r, or x equals 0 to r and then square it. So that's the x-axis setup. This actually works a little nicer, I believe, when you start working it out, because when you get a common denominator over here, you end up with, well, when you square that, you get x squared over r squared minus x squared, and so your 1 becomes r squared minus x squared over r squared minus x squared. So you add those together, and your x squareds add to 0, so you just end up with the square root of r squared minus x squared times r over the square root of r squared minus x squared, and those cancel out. So you are only finding the antiderivative of 1, or of r dx. So I was a little nicer to the right side. Okay. Let's do the setup for the y-axis. Okay. So in this case, we're still using the same function if we integrate with respect to x. If we change everything and integrate with respect to y, you end up with this exact same formula up here. You end up with this exact same setup, except everywhere there's an x, there's a y. But if you integrate with respect to x, then our slices are like this. So there's a delta x. We still have this piece here, but we spin it around this way. Okay, it doesn't go up there really, but now what is the radius? How far does that rotate around? Yeah, it's an x distance. So whether we measure x from here or the middle or over here, in the limit it doesn't matter. So it's going to be about x, so 2 pi x. So this is the radius. And what's this arc length here, or what's that, the approximate value of this piece? It's going to be the same arc length formula that we've been using. So x squared over square root of r squared minus x squared. Write it this way, dx. So this much is our L. Okay? So questions on the setups for either of those? Oh, yes. Thanks. And here, yeah, this is x goes from 0 to x equals r. Because that'll only give me the upper half of this circle, and then I need to get the lower half from that. Okay. Yes? So it should be exactly the same. Unless I made a mistake, which of course I do all the time. But so here this kind of lost my negative, kind of got there. Yeah. So for the x-axis, it's a negative r to r, or you can go 0 to r if you multiply it by 2, because it's symmetric. Okay. Any other questions on this? Yes. It is a negative 2x, but when the first thing I do is take the derivative of this to the 1/2 power, and I get a 1 over 2, and that 2 and that 2 divide out. Yeah. Good question. Other questions? Okay. Thanks for asking those. All right. Well, I brought a surface area of revolution today. Let me see if I can get my webcam up here. So. Okay, I'm going to turn on some lights too. Okay, how did we decide we made this big? Come on, get it. There we go. Got a PhD and 2 master's degrees, and I can't make a window bigger. There we go. All right. Okay, so I brought my surface area of revolution today. It's a flat football. I pumped it up this morning, and it already lost all of its air, almost all of its air. So we live on a surface area of revolution, right? The Earth is somewhat spherical. It's not a perfect sphere. And things, when you live on a surface that's not a Euclidean plane like we're used to working on, things are weird. For example, if you want to take the shortest distance from here to New York, you wouldn't fly. Well, you'd fly up probably over Minnesota to get there. Did you guys know that? Yeah. That's a shorter distance than going around. We won't talk about that today, about why. But here I have an example where I have a dot right over here on this side. See right there, a little dot? This is backwards to me. This is like, oh, come on. It's really hard for me to, there you go. Okay, see that dot? So, and I have one at the other side, right here. So, right there, right there. If you were an ant or you lived on a really big football and you wanted to go from this dot all the way to this dot, what would be the shortest path to get there? So talk to your neighbor. No digging through the football. Okay. Okay. So someone who has a hypothesis, let me know. Or we still have one more surface area problem to do today, but so what's your intuition about what the path you should take? Around? What do you mean around? So like going in a path like this? More or less. Okay. I don't know exactly what you mean, but so a lot of people would think, my intuition is if I could slice this right through the middle of the football and it went through that point and this point, right? If I sliced that football right in half and I went through those 3 points, I would follow that path. Right? Is that what you were thinking? Okay. So I have a string here, and I'm going to put the string through those 2 points, and I'm going to pull it tight. And we're going to see which path it takes. And this is what's going to be hard to see. That's why I put it here. But okay. Is that a straight line? In any place that I turn it, is it straight? It is not. Does not follow that path. So why? And this is the shortest path. If you were on this football, you would not actually want to start ending up. You would not want to start off going from this point right to the center of the football. You'd actually want to start off going this way. And then when you get to the middle, you're going to be heading more straight. And then when you get closer to the end, you're going to head back and back with a tighter curve over to the ball. So why? Anyone have an idea why? Yes. Nice. Very nice. Okay. So let me say it this way, if I can. To go from here to here, you've got to do two things. You've got to go around the football this way, and you've got to go over the football this way. Well, if you've got to go around the football this way, where do you want to do that? Near the ends. So it's a lot shorter to go around the football this way. You don't want to, like a worst option would be like to come over here, walk all the way around the football there, and then back like this, right? It would be shorter to just walk around the end here and then walk around. So you want to spend some of your time, more of your time going around at the ends, and less of your time going around in the middle. So shortest distances on surfaces are called geodesics. So that is the geodesic of a football. Now, what that has to do with surface area, I don't know, other than it is a surface area. But it is really cool. Counterintuitive. If we had a few more minutes, I'd talk about how to use geodesics to minimize hiking between mountains, but we don't have time to do that. So, so we're going to actually find the geodesic, or find the surface area of this football. There. So at least we'll set it up. So I took some measurements and rounded, and in inches, the football, it's about 3 inches in radius, and it's about 12 inches long. So I could set it up. If you're looking at it like this, then you could set it up this way, and then spin it around. Okay. So, what options do we have for finding this surface area of this football? This isn't enough. What do we need to do? Yes? Okay, we might start with a quadratic. It's the simplest nonlinear function we know. This isn't linear. So we've got a point here and a point here and a point here. And if I make the origin right there, then it's going to be ax squared plus 3, something like that. You could also pick another curve like a circle and see if you could approximate a circle through there. Like with the center down here and an arc, right? We could also take more measurements and then do numerical integration. So I could find like every inch, find out what my radius is, and then I could do numerical integration. So, but let's do this for now. So how am I going to find A? Well, the easiest way is to plug in this point here of 6 comma 0. So A equals 6 squared plus 3. Okay, we've got 3 minutes left. See if you can figure out what A is and set up the formula for the surface area of the football. Is it an ellipse? It's not an ellipse, but you could try approximating this curve with an ellipse. So it's spinning out. Is that a circle? I don't know. I have to just I pulled an NFL ball off and a circular part that really right. Yeah. But an ellipse is a circle is just a special area. Yep, we're rotating around the x-axis. Okay, so what would our radius be in this case? If we have an x-coordinate here, how far is that piece going to spin around? 2 pi times that radius, and that radius is the function. So a minus x squared over 12 plus 3. So, and then you've got a crazy trig sub to do to actually do that. Have a great day. Oh, yes. Yeah. Sorry, it took me a second to figure out what you were saying.